Welcome, curious minds, to another deep dive.
Great to be here.
Today, we're plunging into the really fascinating world of digital design.
Specifically, finite state machines.
Exactly, FSMs. If you ever wondered how things like, your phone or even a simple traffic light works its magic,
That intricate dance of electronic?
no, then FSMs are a core piece of that puzzle. We've got some excellent sources lined up.
Really solid material on Mealy and more machines.
And our mission, as always, is to pull out the key insights for you.
Right, so finite state machines, FSMs, they're really fundamental mathematical models of computation, actually.
And they pop up everywhere in digital design.
Absolutely ubiquitous. They give us a structured way to handle sequential behavior, things that happen in order based on what happened before.
Which must make designing complex systems manageable.
That's exactly. Manageable and, crucially, verifiable. You can actually prove they work correctly, which is huge.
Think of them as the brain, maybe, navigating different conditions.
That's a good way to put it. A logical brain making decisions based on inputs and its current situation, its state.
So we'll be digging into the definitions, the characteristics, the real-world trade-offs between Mealy and more types.
And also some important optimization techniques, how to make them efficient.
Okay, get ready, folks.
Yeah.
We're going behind the curtain to understand the logic that powers so much of our digital world.
Let's dive in.
Okay, so let's unpack this FSM idea first. Our sources define them as systems. They can only be in a limited number of states at one time.
That's right, a finite number of states, and they jump between these states based on external inputs.
But why is this model, this state-based approach, so vital? What makes it special?
Well, it really gets at the heart of sequential logic.
Okay. Sequential versus what? Combinational.
Exactly. Combinational logic just reacts to what's happening right now. Think of basic logic gates, A and D, or not. Input changes, output changes instantly.
No memory.
Precisely. Sequential logic, though, its output depends on the current inputs and past inputs.
Ah, the history matters.
It does. And that history, that memory of past inputs, is captured in the system's current state.
And that's usually stored in the hardware.
Typically using things called flip-flops or latches.
Yeah.
Little memory elements.
Got it. And the finite part just means there's a limit to how much it can remember.
Yes. The memory capacity is bounded. It can't remember infinite history. This limitation is actually key.
Why? Seems like a restriction.
Because it makes the system predictable. You can analyze all possible states and transitions. It makes designing and implementing complex behavior much, much simpler.
Okay, that makes sense. Finite states lead to manageable complexity.
You got it.
All right, let's meet the first big player then, the Mealy machine. What's its defining characteristic?
The absolute key thing about a Mealy machine is this. Its outputs depend on both the current state and the current inputs.
Both. Okay, state and input.
Yes, and this has a big consequence. It means that outputs can change the instant the inputs change.
Ah, so even before a full state transition happens.
Exactly. Before the clock might even tick to finalize a state change. This allows for really fast reactions.
So super quick response times. That's a major plus.
Definitely.
I remember reading something about potential downsides. The sources mentioned outputs changing asynchronously. Glitches.
That's the trade-off, you're right. Because the output can change immediately with the input, while the machine is technically still in the same state, you can get these momentary, maybe unwanted output pulses, glitches.
If you're not careful in the design.
Precisely. You have to manage that possibility. Another interesting point is state count.
Fewer states sometimes.
Often, yes. For a given function, a Mealy machine might need fewer states than a Moore machine.
Why is that?
Because the output logic can use the input to differentiate between situations within the same state. It has more information to work with for generating outputs.
Okay, so fewer states potentially, but maybe more complex output logic.
That can be the case. Structurally, you've got your state register, the memory.
Flip-flop.
Right. Then the next state logic, figuring out where to go next.
Based on current state and input.
Yes.
Yeah.
And the output logic, figuring out the output.
Also based on current state and input.
Correct. And crucially, when you design or visualize it, the outputs are associated with the transitions between states, the arrows on the state diagram.
Okay, let's make this concrete. The sources use a great example, the 101 sequence detector.
Ah, yes, a classic FSM example.
This Mealy version detects 101, allowing overlaps, like in 10.101. It uses 3 states, S0, S1, S2.
S0 is like the reset or haven't seen anything useful yet state.
Right. Then S1 means I just saw a 1.
Correct. And S2 means I just saw 10.
And the key part is the output. It doesn't just turn on in a state. It happens on the transition, right?
Exactly. When you're in state S2, meaning you've seen 10,
Right.
and the next input is a 1.
Completing the 101.
Yes. On that specific transition triggered by the 1, the output momentarily becomes 1. The transition itself produces the output. If the input was 0, you'd transition elsewhere, maybe back to S0 with no output.
So the output is tied to the action of moving from S2 with a 1 input, not just being in S2 or the next state S1.
Perfect. That's the Mealy way.
Okay. Now, let's look at the other side of the coin. The Moore machine. How does it differ?
It's a very clear distinction. If Mealy outputs depend on state and input,
Moore outputs depend.
only on the current state. The inputs don't directly affect the output pins.
Only the state matters for the output. What does that mean for timing?
It means the outputs are inherently synchronous with the system clock. They only change when the state itself changes, which typically happens on a clock edge.
Ah, so no asynchronous changes like Mealy.
Correct. Which means...
No glitches.
Exactly. More machine outputs are stable and clean for the entire clock cycle they're associated with that state. Much more predictable timing-wise.
That sounds like a big advantage. Stability is usually good.
It often is. But there's that trade-off again.
Always a trade-off. Let me guess. Speed.
You got it. Because the output only reflects the state after the state transition has fully completed and settled.
It's delayed compared to Mealy.
By 1 clock cycle, typically. The Mealy machine could potentially react within the same cycle the input arrives, while the Moore machine has to wait for the next clock edge to update its state, and then the output reflects that new state.
1 cycle delay. Okay.
Yeah.
And what about the number of states? You said Mealy often needs fewer. Does Moore need more?
Often, yes. Because if you need different outputs, you absolutely must have different states to produce them. You can't use the input to distinguish output conditions within the same state like Mealy can.
So more states might be needed just to handle output variations.
Precisely. Architecturally, it's similar state register, next state logic, but the output logic block, it only gets input from the state register.
Not from the external inputs.
Correct. And when designing, you associate the outputs directly with the states themselves. This state produces output 1. That state produces output 0.
Okay, let's revisit that 101 sequence detector. But as a Moore machine, the sources show it needs an extra state, S3. Why?
It needs that extra state specifically to generate the output.
Because the output can only come from a state.
Exactly. So you have S0, S1, SAW1, S2, SAW10. But when the final 1 comes in while in S2,
Instead of outputting on the transition,
the machine transitions to a new state, S3, on the next clock edge. And it's state S3 itself that is defined to have the output 1.
so you only get the 1 output after you've fully arrived in S3.
Correct. You land in S3, and for that entire clock cycle you're in S3, the output is 1. It perfectly illustrates the core difference.
Mealy, output during transition. Moore, output in the destination state.
Couldn't have said it better myself.
So pulling this together for a designer,
Yeah.
what are the absolute core trade-offs they're weighing up?
It really comes down to a few key things we've touched on. First, output dependence.
State plus input for Mealy, state only for Moore.
Right. Second, output timing. Mealy is asynchronous, potentially glitchy. Moore is synchronous, glitch-free.
And third, response time.
Yeah, Mealy is generally faster to react. Moore has that inherent 1-cycle delay on the output.
Okay, and we also talked about state count and complexity.
Absolutely. Mealy might use fewer states, which sounds simpler, but its output logic, needing both state and input, could actually be more complex to implement.
While Moore might need more states.
Which means more flip-flops, more area maybe.
But its output logic is simpler. Just depends on the state.
Generally, yes. And that often ties into debugging, too.
How so?
Well, the stable, predictable, synchronous outputs of a Moore machine are usually much easier to observe and debug. You know exactly when they should change on the clock edge.
Whereas Mealy, with outputs changing potentially between clock edges based on inputs.
Can be trickier to pin down, especially if you are dealing with glitches or timing issues.
So it sounds like application is key.
Huh.
If you absolutely need the fastest possible reaction.
Like in, say, high-speed data parsing or certain interface protocols, Mealy might be your go-to, despite the potential complexities.
But if you need guaranteed stable outputs for a whole clock cycle.
Like for controlling other synchronous parts of a system or in things like counters where the output needs to be clean.
Moore is often the safer, easier bet.
It often is. It's a fundamental design choice driven by what the system needs to do.
Fascinating. Okay, so you've chosen Mealy or Moore. But the story doesn't end there, right?
Mm-hmm.
Our sources dive into optimization. How do designers make these FSMs even better?
Right. The initial architecture choice is just the start. Optimization is crucial for, well, everything. Efficiency, speed, power consumption, cost.
Making it practical.
Exactly. Making it work well in the real world.
Okay, first up is state minimization. Sounds straightforward, reducing states.
That's the goal. You analyze the FSM and try to find states that are essentially doing the same thing, that produce the same outputs and transition to the same next states for all possible inputs.
Equivalent states.
Precisely. If you find equivalent states, you can merge them into a single state.
And the benefit.
Fewer states means fewer flip-flops needed for the state register. That directly cuts down on silicon area, reduces power consumption, and often simplifies the combinational logic needed for next state and output calculations.
So smaller, cheaper, potentially faster, less power hungry. Sounds like a win-win.
It usually is. Techniques like the equivalence partition method provide systematic ways to find and merge these states.
Okay, minimization is key. Then there's state assignment, or encoding. This sounds like how you actually label the states with binary numbers.
Exactly. Once you have your minimized states, say S0, S1, S2, you need to assign a unique binary code to each one, like 0, 0, 0, 1, 10. And how you choose these codes can have a surprisingly big impact.
How so? It seems arbitrary.
It's not. The choice affects the complexity of the combinational logic the gates needed to calculate the next state, and the outputs based on the current state's binary code.
Ah, okay. The sources mentioned binary, one-hot, and gray code.
Right. Binary encoding uses the fewest possible bits, the minimum number of flip-flops, like 2 bits for up to 4 states, 3 bits for up to 8. It's compact.
But
the logic to decode which state am I in and where do I go next can become quite complex, involving many logic gates.
okay, what about one-hot?
One hot uses more flip-flops, 1 flip-flop per state. So for 4 states, you'd use 4 flip-flops, with only one being hot at any time, like 0, 0, 0, 1000, 0, 100, 1000.
Seems wasteful in terms of flip-flops.
It uses more storage, yes. But the huge advantage is that the next state logic often becomes much simpler. Checking if you're in state S2 is just checking if the third flip-flop is 1. This can lead to faster circuits.
Especially in certain hardware like FPGAs.
Exactly. FPGAs often have lots of flip-flops readily available, so one hot can be very efficient there, leading to higher clock speeds.
And gray code.
Gray code is special. Adjacent states in the sequence differ by only 1 bit. This is useful to avoid temporary false readings during transitions in certain asynchronous or timing-sensitive situations.
So the goal of all these encoding strategies is really
To minimize the complexity of the resulting logic equations. Fewer terms, fewer literals in the Boolean expressions translates directly to simpler, faster, lower power circuits.
right. And once you have those equations, you optimize them too, using K-maps and tools.
Absolutely. Carnot maps, K-maps, are a classic visual way to simplify Boolean logic for smaller problems. For anything complex, designers rely heavily on sophisticated automated EDA tools, electronic design automation.
The software that does the heavy lifting of logic minimization.
Precisely. Applying standard combinational logic optimization techniques to the next state and output logic generated from your state assignment.
And for really pushing the speed limits, the sources mention pipelining and retiming.
Yeah, these are more advanced techniques for high-performance designs. Pipelining is like adding assembly line stages.
Breaking down a long task.
Exactly. You insert extra registers, flip-flops, within the combinational logic paths. This breaks long delays into shorter ones, allowing the whole system to run at a higher clock frequency, increasing throughput.
It adds delay, right? Latency.
It does add latency. It takes more clock cycles for a single input to propagate all the way through, but you can process more data per unit time.
And retiming.
Retiming is more subtle. It involves moving the existing flip-flops around within the combinational logic blocks without changing the overall number of flip-flops or the circuit's function.
I do that.
To better balance the delays between flip-flops. If one path is much slower than others, it limits your clock speed. Retiming tries to even out those path delays, allowing you to potentially clock the entire FSM faster without adding latency like pipelining does.
Wow. Okay. So a lot goes into making these things efficient after the initial Mealy-Moore choice.
Definitely. It's a whole process.
So let's try to wrap this up. Mealy and Moore. Foundational models. Fundamental difference in output generation.
Right. Mealy depends on state and input. Moore depends only on state. That's the crux.
And that core difference leads to all the trade-offs we discussed.
Speed versus stability, state count versus logic complexity, ease of debugging. It's all interconnected. Mealy gives you that immediate reaction, potentially faster,
But you have to watch for glitches.
whereas More gives you clean, synchronous outputs easier to work with.
But with that one-cycle output delay,
Exactly. The choice really hinges on the specific needs of your application.
and beyond that choice, optimization is absolutely key.
Non-negotiable for real-world designs. State minimization, smart state encoding,
Binary one hot, gray, choosing wisely.
followed by rigorous logic optimization, and maybe even advanced techniques like pipelining or retiming for high-speed stuff.
It really is a systematic engineering process to get from concept to efficient hardware.
It is a very structured approach to handling sequential behavior.
So the next time you use, well, pretty much any digital device, remember that hidden dance. States changing, transitions happening, all guided by this logic. Billions of times a second, maybe.
It's pretty incredible when you think about the complexity being managed underneath, and understanding FSMs really gives you a lens to see that underlying structure.
Absolutely. Okay, as we finish this deep dive, here's something to ponder. We're always pushing for more speed and better energy efficiency, right?
Constantly. The two big demands in computing.
So how might those pressures push engineers? Could we see new hybrid FSM designs emerge, blending Mealy and More characteristics in novel ways?
Yeah.
Or maybe entirely different models for computation that go beyond this dichotomy altogether?
That's a great question. Innovation often comes from pushing boundaries and questioning fundamental models. What lies beyond Mealy and More for controlling sequential logic efficiently?
Something for you all to think about. Keep exploring.